Okay, imagine you have a key. Not just any key, not for your front door or your car. Imagine a key that's so powerful it could unlock problems we currently think are just impossible. Things like maybe a real cure for Alzheimer's, or designing a material, like molecule by molecule, that could literally scrub carbon from the air, or even creating a battery that could power a whole city overnight. These aren't just hard problems, they're computationally. Well, they hit a wall. Our best supercomputers today, they just can't handle the sheer complexity. See, our classical computers, even the giant server farms or the chip in your phone, they're incredibly fast calculators, sure, but they work step by step, serially. They're basically checking solutions one door at a time. And if you're trying to model something like a complex human protein, maybe to understand a disease, the number of possible shapes, the number of doors you need to check, it's astronomical. We're talking more possibilities than atoms in the universe. Seriously, there just isn't enough time in the history of everything to check them all one by one. That's the limit. That's the wall. But what if you could build a machine that plays by totally different rules? A machine that doesn't check one door, then the next, but somehow checks every single door simultaneously, all at once. That idea, that massive shift, well, that's the promise of quantum computing.
Right.
That's the key we're talking about.
Exactly. And that's what we're diving into today. We're going to unpack the science, the tech, the big money bets being placed here, try and make this sci-fi sounding stuff actually understandable. And we're going to focus on one company that's taken a really unique path in this whole race, IonQ. So our mission today really is to give you the tools to get your head around this. We need you to grasp one core analogy. We call it the spinning coin that explains the power. And then one core conflict, the tale of two qubits, which shows why IonQ is doing things so differently from, say, Google or IBM. It's really a story about betting on, well, perfection.
Okay, let's do it. So, to understand this battle, this conflict between the quantum approaches, we have to start with the absolute basics, the fundamental unit of information. It's all about the bit versus the qubit. Classical computers, the ones we use every day, they run on bits. It's binary, simple, clean. Think of a light switch. It's either off, that's a 0, or it's on, that's a 1. That's it. No in between.
Right? But a quantum computer, it basically throws that light switch metaphor out. It uses a qubit. And to really, really get what a qubit is, you need that analogy you mentioned, the spinning coin. Think about it. The coin spinning in the air. Is it heads? Is it tails?
Well, while it's spinning, it's kind of both. And neither.
Exactly. It's both. And neither until the very moment it stops, until it lands. That state, that weird fuzzy state of existing in all possibilities at once, that's superposition. So the qubit, while it's in superposition, it can mathematically represent a 0, a 1, and basically everything in between, all at the same time.
Whoa, hang on. We got to pause there.
Yeah.
Because that's tough to wrap your head around. A bit is just 0, O, or R1. A qubit is like the potential for 0, A, and D1, and all the probabilities in between existing together until you measure it.
You got it. That's the core concept. That's the whole game, really. The fact that it's not locked into one state until the very end. That's where the parallel processing power comes from. It lets the machine explore tons of possibilities at once, not one after the other. That spinning coin. That's the heart of the key.
Okay, so that's superposition. But the power, you said, it really ramps up with the second big quantum idea. The one Einstein called spooky action at a distance, right? Entanglement.
That's the one. Entanglement is when you link two or more of these spinning coins, these qubits, together. When they're entangled, their fates become, well, intertwined. If you measure one, you instantly know the state of the other, no matter how far apart they are. It's like they stop being separate things and act as one big, unified, complex system.
Okay. And this entanglement combined with superposition, this is where the exponential power kicks in. Let's make it concrete. 2 normal light switches. How many combos?
4, right. Off. Off on 01, on off 10, on 11.
And a classical computer checks them how?
1 by 1.
Okay.
Step 1, check 0, 0.
Yeah.
Step 2, check 0, 1, and so on. Takes 4 steps.
Okay. Now, 2 entangled qubits.
Because they're in superposition and entangled, that system doesn't need 4 steps. It explores all 4 combinations at the exact same time, instantly, in parallel. No more 1 by 1.
And the scaling. This is where my brain starts to hurt. It's not adding power, it's multiplying it exponentially.
Right. If you can get, say, just 50 really good, stable, entangled qubits working together, that system can explore more possibilities than the biggest supercomputer could calculate in. Well, maybe thousands of years.
50, just 50 qubits.
And if you scale that up to just a few hundred, maybe 300 perfectly entangled qubits, you're dealing with a computational space, the number of possibilities, that's larger than the number of atoms in the known universe.
Okay. That's the scale we're talking about.
That's the power. That ability to handle insane complexity all at once is why people think this is the key to those impossible problems. Drug discovery, material science, massive optimization problems.
Yeah.
Look, this isn't going to replace your laptop for checking email, ever. But it could totally revolutionize how we find new medicines or design catalysts, or maybe even, and this is the scary part for governments, break modern encryption. That's why billions are flowing into this.
Right, the potential is huge. So the goal is clear. Make these stable, controllable spinning coins, these qubits, and link them up. But the massive question, the central fight in the industry is, how do you actually build one? How do you make a physical qubit? And this is where the paths really diverge. The industry is split. This is our tale of two qubits. Two main strategies, and they couldn't be more different.
Let's start with method one. This is the approach the big guys are mostly using: Google, IBM, Rigetti. You could call it the superconducting qubit approach,
Well,
or maybe the racetrack.
racetrack, why?
Well, their approach is really about engineering, brute force engineering almost. They try to build an artificial qubit from scratch. They use techniques kind of like making normal computer chips, but way more precise, to create these tiny, microscopic electrical circuits on a silicon wafer. And these circuits, under very specific conditions, can behave like a qubit.
And those conditions,
Yeah.
that's the catch, right? The cooling.
That's the big one. To get these circuits to show quantum effects, you have to basically stop all the thermal noise, all the vibration. And that means getting them unbelievably cold. We're talking massive refrigerators, these complex dilution refrigerators that cool the chips down to millikelvins, thousandths of a degree above absolute zero. It's literally colder than outer space.
Yeah.
They're constantly fighting the universe's heat to maintain that quantum state.
Wow. Okay, so that sounds incredibly complex and probably expensive. What's the upside? Why do it this way?
Speed. The big pro is speed. Because their electrical circuits, the operations, the gates that manipulate the qubits, are driven by electrical pulses. They happen incredibly fast. Lightning fast, almost.
Okay, speed is good. What are the cons? Sounds like there have to be some.
Oh, yeah. Big ones, stemming right from the design.
Yeah.
Because they're manufactured circuits and need that extreme cold, they are super sensitive. We'd call them high-strung. Any tiny fluctuation in temperature, any vibration, any electrical noise, it can cause the qubit to lose its quantum state, to decohere. This makes them error-prone. Their fidelity, the accuracy of their operations is, well, it's a major challenge. The error rates are relatively high.
High errors. Okay, that sounds bad for complex calculations. And you called it the racetrack. What was the other drawback?
Connectivity. Because these circuits are physically etched onto a flat 2D chip, they're fixed in place, like trains on a fixed track. A qubit can usually interact pretty easily with its immediate neighbors right next to it on the chip, maybe one or two away. But what if qubit number 1 needs to interact with qubit number 50, way over on the other side of the chip?
Uh-oh. You can't just connect them.
Nope. You have to perform a series of swap operations. You move the quantum information from qubit 1 to 2, then 2 to 3, then 3 to 4, all the way down the line until it reaches qubit 50, step by step by step.
That sounds inefficient and prone to more errors.
Exactly. Two big problems. First, it takes time. You're using precious calculation time just shuffling information around, not actually computing. Second, every single swap operation is another chance for an error to creep in. So this limited, neighbor-only connectivity, it seriously restricts the kinds of complex algorithms you can run efficiently.
Okay, so that's method 1, superconducting, fast but high-strung, error-prone, and stuck on fixed tracks. Now, method 2, this is IonQ's approach.
Right. IonQ, which came out of university labs back in 2015, their whole philosophy is different. It's almost elegant. They basically asked, why struggle to build a perfect quantum system when nature already gives us one?
Nature gives us one. What do you mean?
Their qubit isn't a manufactured circuit. It's an atom. A single individual atom that's been ionized, meaning it's had an electron removed, giving it a positive charge. They typically use elements like ytterbium or barium.
An actual atom.
An actual atom. Think about it. Every single atom of ytterbium in the universe is perfectly identical to every other ytterbium atom. Perfect copies made by nature, no manufacturing defects, no variability in the fundamental qubit itself. They call it the perfect sphere.
Okay, so how do they control a single atom? That sounds even harder than the cooling.
It's incredibly precise work, but conceptually quite neat. They trap that single ion inside a vacuum chamber, using carefully shaped electromagnetic fields that basically levitate the atom, holding it perfectly still in space, like a tiny marble floating in a magnetic trap. And then all the control, all the manipulation is done with lasers. Very precisely tuned laser beams act like the computer's fingers.
Lasers do everything.
Pretty much. Different lasers do different jobs. Some lasers cool the ion down, stopping its motion. Other lasers are used to nudge it into that superposition state to get the coin spinning. Another set of lasers can entangle two or more ions together. And then a final laser reads out the result by making the ion glow, or fluoresce, in a way that tells them if it ended up as a 0 or a 1. It's this intricate dance between isolated atoms and focused light.
Wow. Okay, that sounds delicate. And maybe slower, if you're physically moving atoms with light versus sending electrical pulses.
That's the trade-off, generally speaking. The laser operations are typically slower than the superconducting gates. Speed is the advantage Google and IBM have.
So if IonQ is slower, what's the big advantage? Why go through all this complexity with lasers and trapped atoms?
Two huge advantages that directly address the weaknesses of the superconducting approach: fidelity and stability. Because they're using these perfect, identical atoms provided by nature, they eliminate manufacturing errors at the qubit level. And because the ion is floating in a near-perfect vacuum, isolated from almost everything, it's incredibly well shielded from noise and vibration. It can hold on to its quantum state, stay coherent for much, much longer.
And longer coherence time means?
Higher fidelity. Fewer errors. IonQ regularly reports accuracy rates for their 2-qubit operations, the entangling operations of over 99.9%.
Okay, 99.9% sounds good, but how much better is that really than, say, 99%?
In quantum computing, it's a massive difference because errors compound exponentially. Think about a calculation with thousands or millions of steps. If you have even a 1% error rate per step, your final answer is likely to be complete garbage. The competitors, with lower fidelity, they have to dedicate a huge fraction of their qubits, sometimes the vast majority, just to error correction. Constantly checking and fixing mistakes. IonQ's high natural fidelity means they need far less error correction overhead. More of their qubits can actually work on solving the problem.
Ah, okay. So they trade raw gate speed for much higher accuracy and stability, meaning less wasted effort on fixing mistakes. It's a different philosophy.
Exactly. IonQ is betting that for the really hard, complex problems, the ones quantum computers are ultimately needed for getting the right answer, even if it takes a bit longer per step, is more important than getting a potentially wrong answer very quickly. If your calculation is incredibly deep, high error rates make speed irrelevant because the result is useless.
Makes sense. And you mentioned a second huge advantage, something about connectivity.
Yes. This is what many people see as the killer feature of the trapped ion approach. Remember, the superconducting qubits were like trains on a fixed track, limited connections.
Right? Only talking to neighbors.
IonQ doesn't have that problem because they use lasers to control everything, and you can aim a laser beam. You can target any ion in the chain and entangle it directly with any other ion in the chain.
Wait, any ion with any other ion directly?
Directly. This is called all-to-all connectivity. If qubit 1 needs to talk to qubit 100, you just aim the lasers appropriately. Boom. Done. No slow, error-prone swapping down the line.
That sounds like a massive architectural advantage.
It really is. It's like going from that fixed train track to a room full of people where anyone can talk directly to anyone else. It dramatically simplifies how you design quantum algorithms and makes it possible to run much more complex, interconnected calculations efficiently.
Okay, that's a compelling technical case. And we should probably also mention where IonQ came from. This wasn't a typical startup, right?
Not at all. This wasn't cooked up in a garage. IonQ spun out of decades of world-leading academic research from two absolute pioneers in atomic physics and quantum computing, Professor Christopher Monroe at the University of Maryland and Professor Youngsong Kim at Duke University.
So serious scientific credibility from the start.
Absolutely. That deep academic pedigree, that foundation of published peer-reviewed science, gives them enormous credibility in a field that's often filled with, let's be honest, a lot of hype.
Okay, so we have this really elegant science, trapping atoms, manipulating them with lasers, high accuracy, great connectivity. But how does a company doing this kind of, fundamental research actually make money today? What's the business model look like?
Right. It's deep tech, so the path to massive profit is long, but they do have clear revenue streams right now, outlined in their financials. It basically breaks down into 3 pillars.
Okay, pillar 1.
The biggest one currently is quantum computing as a service, or QCSS. Basically, you rent time on their quantum computers through the cloud. Most organizations are going to buy one of these multi-million-dollar machines, especially early on. So IonQ has partnered with all the major cloud providers, Amazon Bracket, Microsoft Azure, Google Cloud. This puts their hardware in front of researchers, universities, companies who want to experiment. It's about access.
Makes sense. Renting time. Pillar 2.
That's the big ticket item. Hardware and system sales. For organizations that need dedicated, guaranteed access, think government labs, major research institutions. IonQ sells them entire quantum computing systems. They have models like their Forte Enterprise. A key example here is the U.S. Air Force Research Lab, AFRL, who bought systems. Selling whole machines is crucial for revenue, obviously, but also for validation. It shows serious players are buying in.
Okay, cloud access and direct sales. What's the third pillar?
Consulting and services. Look, quantum computing is still really new. Most companies, even big ones, don't have in-house expertise. They don't know how to use these machines or even what problems are suitable for them.
Ah, so IonQ helps them figure that out.
Exactly. They provide experts who work with clients to identify use cases, develop algorithms, and translate business problems into quantum computations. We've seen them work with Airbus, for example, on optimizing complex cargo logistics, a classic quantum problem type, and with Hyundai on things like image recognition for self-driving cars. This consulting piece is vital. It helps bridge the gap between the tech's potential and actual business value. It also helps turn those cloud users into potential hardware customers down the road.
So Q and Purbas, hardware consulting, makes sense. When you look at their finances overall, though, what's the big flag, the main risk investors need to understand?
The standout risk, and it's common in these early-stage deep tech markets, is revenue concentration, meaning a very large chunk of their current revenue comes from just a few very large customers.
Yeah.
You're talking about the big cloud providers and those major government contracts like the AFRL deal.
So they have good relationships with important players, which is a positive.
Right, it shows deep engagement. But the flip side is risk. If one of those handful of major contracts doesn't renew, or if a big cloud partner shifts strategy, it would have a disproportionately large impact on IonQ's revenue numbers. It's the nature of a young market with few but very large initial customers. Very fragile in that sense.
Okay. So fascinating science, emerging business model. But this leads into the whole drama around quantum, doesn't it? The market sentiment seems incredibly volatile.
Oh, absolutely. It's a roller coaster. You have this cutting-edge science, huge long-term potential, but also massive uncertainty about timelines and winners. So the market often swings wildly based on news, announcements, or even just comments from influential figures.
Like the whole quantum supremacy thing back in 2019. That seemed to kick things off.
That was a big moment, yeah. October 2019. Google publishes this paper claiming their Sycamore processor achieved quantum supremacy. Their claim was huge. Sycamore did a specific calculation in 200 seconds that, they said, would take the world's most powerful supercomputer 10,000 years.
10,000 years.
Now, it's important to note, the calculation itself was kind of contrived. It was designed to be easy for a quantum computer and incredibly hard for a classical one. A bit of a party trick, as some call it, to prove the concept.
And IBM pushed back hard on that 10,000-year number, didn't they?
Immediately. IBM argued that with better classical algorithms, a supercomputer could actually do it in more like 2.5 days. But in a way, the exact number didn't matter. The psychological barrier was broken. A quantum machine had done something demonstrably faster than any classical machine could. Whether it was days or millennia faster, the point was made. The race was undeniably on.
And that race leads to some wild stock market swings. The Jensen Huang effect is a perfect example, right?
Oh, textbook case. Jensen Huang, CEO of NVIDIA, basically the king of AI chips and parallel processing. His words carry enormous weight.
Oh, first the high points.
March 2024. Jensen gives this interview, praises IonQ's approach, specifically mentioning their work with barium qubits as fantastic, coming from him. That was seen as huge validation for the trapped ion method. The whole quantum sector got a boost, IonQ stock jumped, optimism was high.
And then the other shoe dropped.
Fast forward to January 2025. The same Jensen Huang makes a much more cautious, off-the-cuff remark. He suggests that truly very useful quantum computers, the kind that really disrupt industries, were probably still 15 to 30 years away.
Ouch. 15 to 30 years is a long time in tech investing.
Exactly. He injected a dose of long-term reality, maybe caution. And the market reaction, it was immediate. It was brutal.
Absolute carnage, wasn't it?
Pretty much. The entire pure-play quantum sector just crashed. IonQ took a massive hit, falling over 40% in a single day. Estimates were that something like $8 billion in market value vanished across the industry, just from that one comment.
Wow. It really shows how much of this is driven by hope, expectation, and sentiment about when this technology will actually pay off.
Totally. It's running on fumes of hype and fear sometimes. But importantly, the underlying science is still progressing, despite the market volatility. Just this past October 2025, Google announced another milestone. They moved beyond that supremacy party trick to what they called verifiable quantum advantage.
Verifiable advantage. What's the difference?
This time, it wasn't just a weird calculation. It was a genuinely useful scientific calculation related to material science, something researchers actually care about. And they demonstrated their quantum computer could do it 13,000 times faster than the best supercomputers could simulate it. This felt more real, more practical.
Okay, so real progress. And the ultimate sign that maybe things were shifting, that quantum was becoming, well, relevant, that came from an unexpected source, right?
Yeah, the reaction that really caught everyone's attention was from Elon Musk, not typically someone deeply involved in the quantum discourse, and often a skeptic of overly hyped tech.
What did he say?
When that Google Verifiable Advantage paper came out, his first reaction on social media was just one word. Wow! Then he followed up, replying directly to Google's CEO, saying, "Congrats, looks like quantum computing is becoming relevant."
Becoming relevant from Musk.
That's a signal. Coming from him, it felt like a watershed moment. It suggested the conversation was shifting, even among influential tech figures, from, is this even possible, to, okay, when and how will this scale? It felt like a corner was being turned, moving from pure theory towards tangible impact.
Okay, so we've got the science, the business model, the market drama. Let's try and pull it all together for someone thinking about the space, maybe as an investor or just an observer. What's the core argument for IonQ, the bull case, and what's the opposing bear case?
Right, the bull versus bear. Let's lay it out. The bull case for IonQ really hinges on the belief that their core technology is just fundamentally better for the long run.
How so?
First, superior technological moat. Bulls point squarely at the trapped ion approach. They believe the high fidelity, that greater than 99.9% accuracy, and the all-to-all connectivity are killer advantages. They argue that faster but error-prone machines like the superconducting ones will hit a wall, needing so much error correction they can't scale efficiently for complex problems. IonQ's accuracy and flexibility, they say, provide a better foundation for truly useful quantum computation.
Okay, better tech. What else?
Second, real-world traction. Bulls emphasize that IonQ isn't just theory. They have actual paying customers doing real work. That $25.5 million contract with the U.S. Air Force Research Lab is huge validation. Plus the partnerships with companies like Airbus and Hyundai exploring practical applications. This shows there's demand now, even in these early days.
Got it. Tech and traction. Anything else for the bulls?
Third, the runway. Building this future takes time and money. A lot of money. IonQ has managed its finances to build a substantial $1.6 billion cash pile. It's a war chest that gives them years of funding for R&D. They can weather market downturns and keep investing in their roadmap without facing an immediate funding crisis. They have time to execute.
Okay, that sounds like a solid bull case.
Bob.
Better tech, real customers, and deep pockets. Now let's flip the coin. What keeps the bears up at night regarding IonQ?
The bears look at the same company and see a lot of risk and a valuation that seems way ahead of reality.
Number one concern.
First, massive cash burn. This is unavoidable in deep tech, but the scale is eye-watering. IonQ is deeply unprofitable. Their operating margins have been reported around negative 955%.
Minus 955%. What does that even mean?
It means roughly for every dollar of revenue they bring in, they're spending nearly $10 on operations and R&D. The path to profitability is very long, very expensive, and highly uncertain. They're burning through that war chest and will need to keep raising money eventually.
Okay, huge burn rate. What's the second bear point?
Second, the heady valuation.
Yeah.
Even after market pullbacks, the stock valuation metrics often look extreme. Bears point to things like the enterprise value to sales, EV sales multiple, which has been incredibly high, sometimes cited around 191x.
And how does 191x compare to average?
The average for the broader market might be closer to, say, 4.6x. So 191x suggests the stock price has already factored in massive success and growth for potentially decades to come. The argument is that all the hope for the next 20 or 30 years is already baked into the price. Any slip-up, any delay, any competitor breakthrough, and the valuation could collapse because there's no margin for error priced in.
So, unprofitable and potentially overvalued. Is there a third major risk?
Third, execution and integration risk. IonQ hasn't just been developing its own tech. It's also been acquiring other companies in M&A spree to bring in complementary technologies and talent. Strategically, that makes sense. But trying to successfully integrate different technologies, different scientific teams, different company cultures, while you're also trying to literally invent the future of computing, that creates enormous integration risk. M&A is notoriously difficult even in stable industries. Doing it at the absolute cutting edge of science adds huge complexity and uncertainty. Can they execute on both R&D and integration simultaneously?
Okay, so the bears see high costs, high valuation, and high execution risk. A very different picture.
Absolutely. It really comes down to your belief in the tech's timeline and IonQ's specific approach. At the end of the day, IonQ's story and really the whole quantum computing field right now is a massive bet. It's a bet on those spinning coins, on the physics of trapped ions. It's a bet that accuracy and connectivity will ultimately matter more than raw speed for solving the world's hardest problems.
So it comes back to that key. This is a high risk, potentially incredibly high reward effort to build the key that could unlock those impossible challenges in medicine, climate change, materials science, you name it. And we know now, thanks to things like that verifiable quantum advantage result, that the technology can work. It can beat classical computers for certain tasks. The debate has shifted from if to when, but the big multi-billion-dollar question remains. How long will it take for this technology to scale to the point where it genuinely disrupts a major industry? And which approach, the fast, fixed superconducting track or the slower, flexible, accurate trapped ion method, will be the one to finally, truly turn the lock with a practical, profitable, commercial application? That's the gamble. That's the high stakes game being played out right now. Hopefully, this deep dive has given you a better handle on what those stakes are. Thanks for joining us. Until next time, stay curious.